The Spartan lab is not due yet. Spartan lab will continue tomorrow.
So the midterm is due
Oh,
as well?
actually, some people turned it in already. Yeah. MinTech, yeah, the MinTech, there's not much to do in that lab, right? MinTech, you did 2 calculations. You just compare it to the book's answer. So, okay, so MinTech won't be so. All right, any other questions? No questions. We're going to continue with chapter 19. Just finish it completely. I just want to do like a summary problem. Did we do the calculation where we changed the pressure and the temperature? Okay. Did we calculate the temperature? Okay, good. So we're going to look at, for example, what does, under standard conditions, delta G naught, at 298 Kelvin. If delta G naught at 298 Kelvin is equal to 0, what does that mean? It's at equilibrium. And it turns out that, delta G naught is equal to delta H naught minus T delta S naught. But we also get this. From delta G under non-standard conditions, well, this is delta G under any conditions. If we have delta G under any conditions, this is equal to delta G naught under standard conditions plus RT ln of K. And so what this means is this. If delta G naught under standard conditions is equal to 0, let's take an example of a reaction here. We have a reaction where we're going to have NO, 2 NOs plus an O2 goes to NO2, 2 NO2. So we looked at the kinetics of this reaction, but now we're going to focus on the thermodynamics of this particular reaction. And kinetics is just how fast the reaction occurs. Thermodynamics is the driving force for this reaction. And so if we have a delta G naught, this is going to be at 298 Kelvin, is equal to 0. And everything else is at 298 Kelvin. This is at 298 Kelvin, this is at 298 Kelvin, and the temperature is at 298 Kelvin. That means there's no driving force for this. And so the way we can visualize this is if delta G naught is greater than 0, then the reverse reaction is spontaneous, right? Reverse. If delta G naught is equal to 0, then we're at equilibrium. If delta G naught is less than 0, then we have driving force for the forward reaction. The reverse reaction. So right now, delta G naught's equal to 0, so this system must be at equilibrium. But we know something here. We know that under standard conditions, what does that mean, standard conditions here? All right, first, is there a standard temperature? Is the standard temperature 25 degrees C, 298 Kelvin? Yes? No. There's no standard temperature. The only thing is, yeah, the concentrations are 1 molar and the pressures are 1 bar or 1 ATM. Our book uses bars, so we'll use bars. In other books, they use ATM. And so this means under standard conditions, at 290 Kelvin, it's equal to 0. Right? And so that means here that, that if I say the initial was at 1 bar, and 1 bar, would this be under standard conditions?
Yes.
Yes, this is under standard conditions here. If delta G naught equals 0, then that means there's no driving force. That means I must be at equilibrium. And so I must be at equilibrium here. In other words, if I look at this, delta G under any conditions, if I just set that equal to 0, so that means I'm at equilibrium. So delta G under any conditions, if I'm at equilibrium, then I have this. Or if we go back to this, actually, let me go back to this for a second. Another way of thinking about this is we have Q. Q is the reaction quotient, and so we're looking at the initial conditions using Q, and we compare that to K. And so we're going to see there's going to be a relationship here with K. And so if we have delta G naught equal to 0, that means Q is equal to K. I'm already at equilibrium. Equilibrium. And then I can see the relationship here between delta G naught and Q. If I'm already at equilibrium, then that means K must equal 1. Because Q is just the activities. Q is going to be the activities of the products that are given divided by the activities of the reactants. Initial, raised to their respective power. K is the same thing. K, this is called K, the thermodynamic K, which is KEQ. That's the activity of the products raised to the respective power and activity of the reactants. And so if delta G naught is 0 at 298 Kelvin, what this means is that if I start off with 1 bar or 1 molar, and I'm going to get a Q of 1 because the product here, you know, of gases will be the pressure. If we have some aqueous solutions, it would be molarity. If we have solids or liquids, those would be 1. And so, in other words, Q is equal to 1. So if there's no driving force here, then Q must equal K, therefore K is equal to 1. Right? Otherwise, I'd have the driving force. So under standard conditions, which are these, and delta G naught at 298 Kelvin is 0, then K must equal 1 at 298 Kelvin. Right? If K is equal to 1, we'll plug in 1 up here. If K equals 1, then this is 0, and delta G is equal to delta G naught, which is equal to 0. So I'm good here. But how many reactions have a K at 298 equal to 1? If you look at all the K values that you did the ICE tables for, did you see very many of them with a K equal to 1? No. In fact, is K equal? Can I have delta G naught equal 0 at 298 Kelvin for this? And so let's take a look at this specific reaction. So if delta G naught at 298 Kelvin equals 0, then this is already at equilibrium. And there's no need to do an ICE stable reaction because Q is equal to K, we're at equilibrium, no change. If delta G naught at 298 Kelvin is not equal to 0, then this is not at equilibrium, and we expect either forward or reverse reaction to occur depending on if Q is greater than K. Actually, go back over here. Over here, delta G not greater than 0 means Q must be greater than K. We have too much product. Reaction's got to go reverse. If delta G naught is less than Q, then that means Q must be greater than K. We need forward reaction to occur. So let's take a look at this reaction and see what it is. So we'll go 2 NOs plus an O2 yields 2 NO2 gas. Under standard conditions, we know everything's going to be at 1 bar, so these are gases. So we say this is under standard conditions here. Then we pick a temperature. Well, the temperature is going to be at 298 Kelvin. And let's see what our delta G naught is. And so what's the easiest way of calculating delta G naught at 298 Kelvin? The easiest way of calculating delta G naught at 298 Kelvin is by using the sum of the delta G naughts of formation of the product minus the sum of the delta G naught of formation of the reactant. So if I look at the product, I have 2 moles of NO2 times the delta G naught of formation of NO2, 51.31 kilojoules per mole. Would be for NO2, my product, minus the sum of the reactants. Well, I have 2 moles of NO. Let's see it. And for NO, it's 86.55. The second column is delta G naught formation, 86.55. Okay, minus the delta G naught of formation for O2. Do you know what the delta G naught of formation for O2 is? You should know. It's going to be 0. So it's because the formation reactant is the formation of O2 from O2, so it'll be 0. This will be O2. So what does our delta G naught come out to? Negative 70.48. Okay, this is kilojoules. This would be kilojoules per 2 moles of NO2 because it's kilojoules for the reaction as written. And so it's not per mole, but it's going to be per 2 moles of NO2. I'll just leave it as kilojoules because it'll be easier. And so when we see that, what does this tell us? That there's a driving force, right? There's a driving force for forward reaction. And so that means under standard conditions here, this is not at equilibrium, right? If this were at equilibrium, that is, if my initial conditions here, the standard conditions, were my final conditions, the equilibrium conditions, then delta G naught must be 0. But here we see it's not 0, so there is a driving force. In other words, this tells us that Q, my initial conditions are too small. My Q is less than K, so I got to have forward reaction occur to reach equilibrium. For
forward reaction, Q has to be greater than K.
For forward reaction, Q has to be less than K. Oh, was I? Okay, sorry. Can you fix that? For reverse reaction, Q is greater than K. Well, this is a delta G formation here. So I expect forward reaction. So you know what? The standard conditions are not at equilibrium. I'm going to expect some forward reaction to occur. Now, what does the magnitude tell me? You know, how much forward reaction should occur? You know, how big of a driving force is this? You know, and so in other words, what are the ranges of delta G's we expect? And how does that compare to this? Because I know that this is not my equilibrium conditions. There's got to be some kind of change here. And so the easiest way to do that is to look at the relationship between delta G naught, or delta G and K. So if we look at the relationship between delta G naught and K, then we could see that over here, because if we're at equilibrium, you know, delta G is equal to delta G naught plus RT ln of Q. If we're at equilibrium, then we know that delta G under any conditions at equilibrium is going to equal 0, which is going to equal delta G naught plus RT ln, and now Q goes to K, because at equilibrium Q is equal to K, let's say those conditions are at equilibrium. And that means that delta G naught is equal to minus RT ln of K. So if we want to figure out the relationship between delta G naught and K, we can do it here. We'll just pick some delta G naught values and then compare it to the K value we get. We're going to solve this equation for K. K is going to equal e to the minus delta G naught over RT. We'll use this equation to solve for it. And so if we have a delta G naught equal to 0, let's say plus 50, plus 100, plus 200, and then we'll go minus 50, minus 100, minus 200. You know, so we're here at minus 70 down here between minus 50 and minus 100. And so we'll get some values here. These are going to be values in kilojoules. And we'll calculate our K. So delta G naught equals 0. We'll plug that in here. E to the 0 is just equal to 1. So if delta G naught is equal to 0, there's no driving force. So our standard conditions here are just the equilibrium conditions. How about delta G naught of plus 50? So a delta G naught of plus 50, we'd convert that into joules. So it would be negative 50,000 joules here. So let me just plug that in. Negative 50,000 joules divided by R, which is 8.3145 joules per mole Kelvin, or joules per Kelvin, divided by T, which would be 298. And then raise it to the E. Actually, I don't know how to use this calculator. Does someone have it?
Yeah, 1.7 times 10 to the negative 9.
Times 10 to the negative 9? Okay, let's go plug in 100,000 here. So we go minus 100,000 divided by 8.314 divided by 298. Raised. Okay, now change it to 200,000 joules. And the negative 36. Okay. All right, now let's go the opposite way. Let's go to 50,000 negative. So this is going to be positive 50,000 divided by 8.314 divided by 298. Raise that. You raise E to that. And then let's go to 100,000. And then 200,000. All right, take a look at these numbers here. And we'll see, you know, a positive delta G means it's non-spontaneous, right? It's non-spontaneous, but if you look at it, a delta G between plus 50 and minus 50, we have some sort of equilibrium, you know, between product and reactant. And the more positive we get, the more we favor products at equilibrium. And so it's going to have a K greater than 1, more products and reactants. The more negative we get, we favor reactants. But between plus 50 and minus 50, you know, you're going to expect significant quantities of both product and reactant. As you go over here, you know, this is all reactant, and as you go down here, this is all, pretty much all product. And so we have different degrees. Just because it's positive doesn't mean everything's going to react. We're going to hit some kind of equilibrium, right? And so we see this delta G. This delta G is negative, so we have a driving force. It's pushing the reaction forward, right? It's pushing the reaction forward, so let's go ahead and calculate our K value for this. K is equal to E to the minus delta G naught over RT. And so plug in K, which is going to be 70,480 joules. And the negative times the negative gives us positive. Divided by RT, raise it to the E power. What do we get for K? .12?
No.
Oh. try this calculation again. 70,000. Yeah, you got to convert it to joules. So 70,480 divided by 8.3145 divided by 298. Okay, 2.25 times 10 to the positive 12. Which means this highly favors product. This is a pretty big driving force. And are we anywhere near that? We're starting at standard conditions. Are we anywhere near that? No. This has got to form a lot of product. And so, okay, we'll start off in standard conditions here, and we see we're far from equilibrium. And we can see that we're far from equilibrium because our delta G naught value is minus 70. You know, we expect a lot of product in this. You know, if our delta G naught value was like +1 or +2 kilojoules, then maybe we're pretty close to equilibrium, right? But here, no. Or -1 or -2. Here we're far from it. And so what's going to happen is there's going to be a change, right? There's going to be a change to get to equilibrium. This is the driving force for the reaction. That change is going to be, okay, we're going to have minus 2x bar, minus x bar, plus 2x bar. And so at equilibrium, we expect 1 minus 2x bar, 1 minus x bar, and 1 plus 2x bar. And so we know that K is equal to this. Well, K is going to equal, this is a thermodynamic equilibrium constant. And so that's going to equal the activity of the products over the activity of the reactants. And so it's going to be the activity of NO2. Well, NO2 is a gas, so the activity is just equal to its pressure. And so we're going to get the partial pressure of NO2, and it's going to be squared, divided by the activity of the reactant. So it's going to be the partial pressure of NO squared, divided by the partial pressure of O2. And so since these are all gases, then KEQ is equal to KP in this case. If these were all aqueous solutions, then KEQ is equal to KC. We just plug in the molar concentrations. Or if it's heterogeneous, it's a mix, then KEQ is neither KC nor KP. We just look at the activities of each. And so it'd be a mix of molarities and pressures. So we see that, well, we're kind of far, so we're going to try to reach equilibrium by shifting or going forward. There's going to be a driving force for forward reaction. We got to reach equilibrium. And so we'll take these in here and plug that into this to do an ice calculation. But is this the best setup for an ice calculation? No, what would you do? You would reset this, right? This is way too hard, calculation. So let's go ahead and reset this. We need to reset it. We reset it to the left or we reset it to the right? Which way do you want to reset it? To the left or to the right? We don't want to reset it to the left. We want to reset it to the right. Why? Because K is big. It's mostly products. And so we reset it to the right, which means our new initial will be what? Okay, the NO, does that go to 0? Well, it depends on what is our limiting reagent. If we were to reset this to our right, is NO the limiting reagent or O2 the limiting reagent? Can you do this one in your head, or should you do a Chem 1A style stoichiometry problem? You might be able to do this one in your head, because if we have one O2, how many NOs do we need? 2. Do we have 2? No, so what's our limiting reagent? NO. Or if we have one NO, then we need half an O2. Well, we have more than a half an O2, right? And so NO is our limiting reagent. Our limiting reagent is going to go to 0. And so that means we're losing, remember I used Y for this, minus 2Y. That means 2Y is equal to 1. That means Y is equal to 1/2. So this is going to be minus Y, and this is going to be plus 2Y. So if Y is 1/2, then this is going to go to 0.5 bar, and this is 1/2 times 2. This is going to go to 2 bar. So this would be my new reset initial conditions. I reset it to the right because K is big. And then let's do it, the change in equilibrium. So this is going to be plus 2x bar, plus x bar, minus 2x bar. And so I'll get 2x bar at equilibrium here, 0.5 plus x bar here, and then 2 minus 2x bar here. Okay, now let's solve for x. So we solve this for x. We get the k is equal to that. So 2.25 times 10 to the positive 12 is equal to 2 minus 2x quantity squared divided by 2x quantity squared to the 0.5 plus x here. We use a simplifying assumption here, the SA. 2 minus 2x should just go to 2. And then 2x stays. And 0.5 plus x will just go to 0.5. We'll just say x is much smaller than 0.5. Okay. And then solve this for x. So what does x equal here? I'm kind of ignoring sig figs because we'll just call those exact. So about 9.42 times 10 to the minus 7, is that what you got? Vaughn, you got 9.42?
9.43.
All right. Yeah, we're not going to round it up there. Leave it. Anybody else? No. We'll go with this here. Yeah. And so that means at equilibrium we have 18.8 times 10 to the minus 7 bar. And then 0.5 plus x. 0.5 plus x, is it really going to have much impact on 0.5? No. This is going to be about 0.5 bar. 2 minus 18.8 times 10 to the minus 7 is just going to be about 2 bar. Yeah, so the simplifying assumption was pretty good in this case because it was pretty negligible change. And so, but we need to check out K. Does K work? And so we should double check this to make sure K is okay. Is it? Does it check out? So, 2.26 times 10 to the 12? Okay, then it checks out. So this is good. And so when we have the negative 70 kilojoules as our delta G, that means there's a pretty big driving force, right, for the forward reaction. We're far from equilibrium. So there's a big driving force. And so one of the things we can do is we can figure out what is the percent reaction here. And so how much of our original 1 bar reacted? So the percent reaction is going to equal 100% minus the percent remaining. The percent remaining we can calculate is just the amount that remains, 18.8 times 10 to the minus 7 divided by 1, the initial amount, right? Times 100. And so this comes out to 18.8 times 10 to the minus 5. Times 10 to the minus 4. So any 3's 9. So this is going to come out to 99.99912% reaction. You see, so you know this is a big case. So you know this is far from equilibrium. So we're going to expect most of it to react. Now tell me this. What happens if I change the temperature? In other words, let's say if I increase the temperature, can I get a higher percent reaction? I'll just increase the temperature to try to go for maybe 99.9999% reaction. Would that work? So what happens if I change the temperature? So if I increase the temperature, will I increase the percent reaction? In other words, if I increase the percent reaction, I would need a bigger K, right? That is, will K be bigger? Will I increase K? And then you think back at your reactions, well, or your equations. Delta G naught is equal to minus RT ln of K. And I go K is equal to E to the minus delta G naught over RT. So as the temperature increases here, then what should happen to K? As the temperature increases, this becomes bigger, which means this whole thing becomes smaller. Well, it makes the denominator smaller, which means it becomes, K becomes bigger. And so does K become bigger? We don't know. Don't know because K depends on temperature, but also delta G naught depends on temperature. In fact, we could actually change the sign of delta G naught by changing the temperature sometimes, right, in certain reactions. And so we can't. In order to use this equation, we would have to know what the temperature is and what delta G naught at that temperature is. And so let's look at what happens so let's see what happens with delta G naught. Delta G naught is equal to delta H naught minus T delta S naught. And so what happens with delta G naught with temperature? As I change the temperature, let's say I increase the temperature, does delta G naught become more favorable or less favorable or stay the same? How can I see what happens with my delta G naught? Well, the way I calculated it is not going to tell us anything because my calculation of delta G naught was based on delta G's of formation at 298 Kelvin. And so I have to see how delta G naught changes with temperature. One way to do that is to look at the reaction here. Delta H, is it exothermic or endothermic? Can you look at this reaction and tell me, what do you think? Is it going to be an exothermic or endothermic reaction? If you look at this reaction, we're combusting. This is a combustion reaction. So we're combusting NO, we burn it completely to NO2. And so combustion reactions are typically exothermic or endothermic? Exothermic. And so delta H is less than 0. That's favorable. How about delta S? Yeah, delta S is going 3 to 2, which means it's not favorable. And so in this particular scenario, we say that this is spontaneous at low temperature. So if I want a higher percent reaction, then what I need to do is to lower the temperature, not raise the temperature. Because lowering the temperature will make delta G naught more negative, which is going to make K bigger. So the more negative this becomes, negative times a negative, this becomes more positive. And these temperatures have to match. This is delta G naught at that temperature, which is this temperature. So we can also see that here. So let's go ahead and calculate what our delta H naught and our delta S naught are. And so we know it's going to be exothermic, but we can do the calculation from appendix D data here. So we'll take our delta H, the products, 33.18 times 2. For NO2 minus the reactants, NO. Which is 90.25, 2 moles. And then 0 for O2. And so delta H of this reaction is equal to this. So what does it come out to? We have 66.36 minus 180.5 minus 114.14. So this is kilojoules per 2 moles of NO2 form, not per mole. And let's calculate our delta S naught. We have 2 moles of NO2. Let's see what the entropy for that is. Entropy is this last one here, 240.1. Let's say absolute entropy. 240.1 is going to be joules per mole Kelvin minus entropy of NO. Put back here. $210.8. So we got 2 moles at 210.8 joules per mole Kelvin. How about the entropy of O2? Is that 0? The delta H of formation is 0. Yeah, but the entropy is not. What is it? 200 something. Yeah, it's 200 something. We can find out. I'll let me know. Let's go to 205.1. So we have 1 mole of O2 at 205.1 joules per mole Kelvin. So let's see what this comes out to. Units here would be joules per Kelvin for the formation of 2 moles of NO2. This is going to be -0.1465 kilojoules. Or, actually, let's see, do we want to go convert it? No, we'll just leave it. And so we plug this in here. Delta G naught is equal to delta H naught, which is minus 114.14 kilojoules, minus T delta S. Well, delta S is going to be minus 0.1465 kilojoules. And so here, this is minus 114.14 kilojoules. Minus a minus, it gives us plus T times 0.1465 kilojoules. So here we can see, as we increase the temperature, what's happening to delta G naught? As we increase the temperature, this is becoming more positive, which is canceling this out, right? And so increasing temperature means delta G naught is going to be increasingly positive. And so a more positive delta G naught favors reactants, right? And so we're going to get less reaction to occur. And so what we need to do is we need to decrease the temperature. And so the more smaller the temperature we make, the more negative this delta G becomes, and the more forward reaction we expect. That is, K is going to be bigger. Okay. Yeah, increasing temperature means increasing delta G, which means less reaction. This is increasingly positive delta G. So decreasing means decreasing delta G, that is making it more negative. More reaction. So if I wanted to increase the percent reaction, I would lower the temperature, not raise the temperature.
When you got new pressures, how do you check if K works?
How do you check if K works? For which one?
For when you got the new pressures.
When we get the new pressures, how do you, oh, you just plug it in. This is the equilibrium pressure of NO2. So that's going to be 2 squared. And this is the equilibrium of NO, so this is 18.8 times 10 to the minus 7 squared. And then the O2 is just raised to the first power, 0.5. We'll multiply this out and see if that matches our K value, 2.26 times 10 to the 12. Okay. And it does. Or came out close. 2.25 was our K value. I think that came out to 2.26. All right, so what we're going to do now is we're going to ask ourselves this. If I keep increasing the temperature, I'm going to reduce the driving force. Is there a temperature at which I can cancel out that driving force? That is, I can make this term big enough so that it cancels out this term here. Is there a temperature? Yeah. Okay, right now this is a spontaneous reaction. And so what I'm asking is this. Is there a temperature that, that can make this reaction non-spontaneous? And the answer is yes, yes. And so the question is, at what temperature will this go non-spontaneous? And so what we want to do is we want to cancel out the driving force. And it's possible at this, because this is spontaneous at low temperature, non-spontaneous at high temperature. So what is high temperature? Well, that's what we're going to calculate, because right now it's at room temperature, it's spontaneous. And so how are we going to do that? Well, what we want to do is we want to get this term, the second term, to cancel out the first term. And so in other words, to make this non-spontaneous, delta G naught is going to equal 0. That is, you know, we start off at 1 bar, 1 bar, 1 bar, and we expect no driving force. It should just stay as 1 bar, 1 bar, 1 bar, right? In order to do that, we're going to say that delta G naught is at equilibrium. This is going to equal delta H naught minus T delta S naught. In other words, this first term, which is driving force, is going to be canceled by the second term, which you can call like the anti-driving force or whatever. And so if we have negative 114.14, we need positive 114.14 here. They'll cancel out the 2. And so we could calculate what temperature will do that just by solving this equation. So delta H naught is equal to T delta S naught. In other words, the temperature is going to equal delta H naught divided by delta S naught. Then we're going to make an assumption. We're going to assume that, you know, these also have to be a temperature T, but we're going to assume that the 298 values will be close enough. So this is going to be 298 Kelvin delta H naught over delta S naught at 298 Kelvin. Yeah. Well, we just calculated those. And so delta H naught was 114, negative 114.14 kilojoules. Delta S naught is kilojoules per Kelvin. Would be negative 0.1465 kilojoules per Kelvin, which gives us what temperature? 779.1 Kelvin. So if we bump up the temperature to 779.1 Kelvin, then this negative 114 is canceled out by positive 114 here. And therefore we'll get delta G naught equals 0. In other words, this will be at equilibrium. And so what does that mean when delta G naught is equal to 0? That means that standard conditions are equilibrium conditions, right? And so when delta G naught is equal to 0, that means that the standard conditions are equal to the equilibrium conditions. In other words, the standard conditions, which is what we're given, you know, we're given standard conditions, Q is equal to K. What is Q here under standard conditions? Everything is 1, therefore Q is equal to 1, which means K must equal 1. And so what we did was we just changed the temperature. Right now the Q is like 10 to the, K was 10 to the positive 12, but we changed the temperature so that K equals 1, because K depends on temperature. K changes with temperature. And so all we're doing is we're altering our K value so that, it matches our standard conditions here. But this isn't happening at room temperature. This is going to be at 779.1 Kelvin. And so I kept increasing the temperature until this happened. Well, there's another way of looking at this, and the other way of looking at this is this. Or we could have looked at this. If we look at delta G is the driving force under any conditions. The driving force under any conditions is equal to the driving force under standard conditions plus this correction, RT ln of Q. If we say that we want this to be at equilibrium, we want no change, delta G is equal to 0, then this is equal to delta G naught plus RT ln of Q, and then we solve this. Delta G naught is equal to minus RT ln of Q. Well, this is at equilibrium, so Q is equal to K now. So we get delta G naught is equal to minus RT ln of K. And therefore, if we solve this for temperature, temperature is equal to delta G naught over R ln of K, and we need the negative signs. So will this work? So for example, I had earlier we had calculated our delta G naught. Our delta G naught was minus 70. Was it minus 70? .48 kilojoules. Will this work? This will not work. Why will this not work? Because that's the delta G naught at 298 Kelvin. We can't use the delta G naught at 298 Kelvin. We need to use the delta G naught at the temperature of interest. Actually, now we know what it is, but we don't necessarily, because this is an alternate way of calculating temperature. And so we can't do it like this. However, we can do it like this. And so this is going to be a dead end because this is going to be delta G naught at that temperature. And so what we're going to do here is this. We're going to say that delta G naught is equal to minus RT ln of K, which is equal to delta H naught minus T delta S naught. And so what we're going to do is we're going to add a T delta S to both sides. So if we add a T delta S to both sides, we're going to get T delta S naught minus RT ln of K is equal to delta H naught. And then we're going to factor out a T here. So T times delta S naught minus R ln of K is equal to delta H naught. And then divide by this. And so we end up with T is equal to delta H naught over delta S naught minus R ln of K. Here. Now what we can do is this. What do we want K to equal so that there's no driving force here? We need K equal to 1. And so what we'll do here is we'll plug in K is equal to 1. When we plug in K equals 1, ln of 1 is 0, and T is equal to delta H naught divided by delta S naught. We'll assume that 298 is okay, and so we get the same temperature as we should. And so two ways of approaching it, because when we are at equilibrium under standard conditions, then we know delta G naught is equal to 0, or we want a K value equal to 1. Okay. That way, under the standard conditions, nothing's going to happen. And so if we increase the temperature, we'll decrease the driving force and also decrease K until the point where K is equal to Q, or starting here. But this gives us a way to manipulate the reaction. We could have any amount, you know, from 0 to 99.99+% by changing the temperature, I think. We could have 0% reaction, right? 0% reaction if the temperature is 779. And so what we might do is we might just pick, you know, percent reaction. And so the percent reaction we're going to pick is something like this. I'm going to start off at standard conditions, and I'm going to go at what temperature the next example. At what temperature will I get 50% reaction? And so what I want this to do is I want just half of it to react and then stop. Is it possible to do that? It turns out, yes, it's possible. We just have to make sure we stop at equilibrium, which corresponds to 50% reaction. And so if we start off with standard conditions and I want 50% reaction, I look at my limiting reagent. The limiting reagent's NO, so I'll say minus 50% here. And if I lose 50%, I'm going to end up with half a bar. So half of it's gone. So now I have 50% reaction. 50% reaction. So if I lost 50% of this, how much will I lose of the O2? 25%, which is going to give me 0.75 bar. And then I'm going to gain 50%, and so over here I'll have 1.5 bar. And so this would be 50% reaction. I need it to stop here. How can I get the reaction to stop here? Well, I make this the K, you know, because all the reactions are going to go until they reach equilibrium, which is K, the correct ratio of products to reactants. And so if I want this K value, then I'm going to have to do 1.5 as my equilibrium NO2 pressure squared. So I need the parentheses for that. Divided by 0.5 squared divided by 0.75. And so I need to make this my K value here for 50% reaction. And so we know that K changes with temperature, so hopefully I can achieve this K value with just a change in temperature. And so this is going to be 1.5 squared. And the K value is 12. So I want a K value of 12. And so the question I need to ask myself is, at what temperature will I get a K value of 12? And if I could get the K value to 12, then this will be my equilibrium ratio here. And so how can I figure that out? Well, I can use different equations. For example, this one, K is equal to minus delta G naught over R ln, oops, no, e to the minus delta G naught over RT. Will this equation work? Well, actually, no. I don't want this equation. I have to rewrite this for T. T is equal to minus delta G naught over R ln of K. I know my K value. Just plug that in. Here, will this equation work? No, why not? Yeah, right. Delta G depends on temperature. I don't have this. This is unknown, so we can't use this equation either. What equation are we going to use? Well, we might be able to use this equation here if we make some rearrangements. Right? The rearrangements would be like this. Delta G naught is equal to minus RT ln of K, which is equal to delta H naught minus T delta S naught. And then solve this, and we end up with that equation there. T is equal to delta H naught over delta S naught minus R ln of K. This works because delta H at 298 Kelvin, we know, and it's close to whatever temperature this comes out to. It doesn't change much with temperature. And the K value is what we want, a K value of 12. So we plug in the K value here, 12.0. We plug in our delta H naught and our delta S naught, and then solve for T.
What's the R value?
3145. 8.3145. .48. Kelvin. Oh boy. So if we want 50% reaction, we would have to cool this to 5.48 Kelvin. Is that right? Because the colder this reaction gets, the more percent reaction we have. And so I think it has to get warmer than room temperature. So there must be some error somewhere. I'm not sure. Let's see if we can figure it out. Okay, what did you put for delta H? Delta S?
0.1465.
Oh, kilojoules?
Yeah.
Let's go with joules. It'll be easier. 114,140 joules. And then this was, how How many joules?
Negative 146.
Oh, for the delta S.
Yeah, negative 146.5.
Negative 136.5?
146.
146.5 joules. Okay, minus 8.3145 ln. This is going to be joules per Kelvin. This is joules per Kelvin. Ln of 12.
Six,
682.8. All right, so this is, in this particular case, we increase the temperature to get less reaction. And so we'd have to increase it. At room temperature, we had like 99.9, 290 Kelvin. If we increase the temperature closer to 680, closer to 700 Kelvin, then we're going to get less reaction. And so according to this calculation, if we can increase the temperature to 682.8, that's going to give us a K value of 12, which means in this particular reaction, we'll get 50% reaction, and then it hits equilibrium and won't react any farther. So we can convert half of our limiting reagent in this particular example. And so this just shows, we can use temperature to manipulate the driving force. And also a little bit about what it means. And so let's do a little conceptual check here for this. I could get whatever percentage. If I wanted 25% reaction, it gives me a different K value. If I want 90% reaction, it gives me a different K value. So I can just use temperature to change the K value to get the desired amount of reaction I want. If I want to maximize the amount of reaction, then I'll lower the temperature. But if I lower the temperature, what's going to happen to the kinetics, though? It gets slower. So I'll make more product, but it's going to just take longer to make it. That's all. Okay. Now, let's go through some conceptual questions here. If delta G naught is equal to 0, what can you tell me? If delta G naught is equal to 0, what does that tell you? K is equal to Q, which is equal to 1. Right? Is the temperature at 298? Hey, this is standard conditions. Is the temperature at 298 Kelvin? No. No, it's most likely that the temperature is nowhere near 298 Kelvin, because at 298 Kelvin, how many Ks have you done an ice calculation equal to 1? Probably 0. And so it's likely, to have a delta G naught equal to 0, the temperature is nowhere near 298. It's got to be way high or way low. Because in order to get an equilibrium condition, what are my equilibrium concentrations, pressures? Everything's at 1, right? Which is unusual, right? And so this is why this. And so it's going to be at whatever temperature T that is. There's going to be some temperature T, and T is not standard. If delta G is equal to 0, what can you tell me? Can you say that Q is equal to K, which is equal to 1? Does that work? If delta G is equal to 0. If delta G is equal to 0, then can you say that Q is equal to K? I mean, is there a driving force? Like for forward reaction, or driving force for reverse? In other words, are we going to shift the reaction to the right or shift it to the left? No. And so Q is equal to K, but we don't know what K is because this is under non-standard conditions. And under non-standard conditions, the pressures can be anything And the concentrations can be anything. Right? And it might just happen to be. If the pressures and the concentrations roll out 1, and delta G is equal to 0, then that means delta G and delta G naught are the same thing, right? Because K is equal to 1, because delta G is equal to delta G naught plus RT ln of K, and if K is equal to 1, then that falls out, right? And then the standard and the non-standard are the same. Okay. And so some of the tricks to chapter 19 is the temperature always gets people, because we have to keep track of the temperatures, especially for delta G. Delta G changes with temperature. But otherwise, the calculations, some people would say the calculations are pretty straightforward. Any questions on this?
So under non-standard, K will still be equal to 1?
If delta G is equal to 0, and the given conditions were standard conditions, but no, typically not. Yeah, K is not equal to 1. Okay. And so the K value relationship that we calculate is K versus the driving force versus the standard conditions. But we don't have to start under standard conditions. We could start under any conditions. And so we could do an example of that now. Let's do that. I'll do, to keep the calculation, okay, let's do 2 bar here, 1 bar here, 2 bar here. Now, am I under standard conditions? No. So I'm under non-standard conditions here. We know that under standard conditions, delta G naught was minus 70.4, whatever. But this one, well, I can't say delta G naught, right? This one is not under standard conditions, so I'd have to say delta G. But delta G is equal to delta G naught plus RT ln a Q. Well, this is going to be at 298 Kelvin, so we'll do this at 298. Make it simpler. All right. So what we're going to do is we're going to calculate just delta G. It would be K here if it were equal to 0. But we don't know if it's equal to 0 or not. And so let's calculate it. And so what was delta G naught? It was minus 70.48 kilojoules plus RT ln of Q. And so T is 298 Kelvin. Q is, well, that's going to be 2 squared divided by 2 squared divided by 1. Which equals 1. So in this case, if Q is equal to 1, then ln of 1 is 0, and we get that this is at negative 70.48 kilojoules, which means we're far from equilibrium, and we got to do the same thing, right? Change Q. Well, it came out negative 70.48, which means we're going to have the same K value, correct? As before. All right, let's do something else here. rather than having this at 2 bar, let's do another example where this is at 0.1 bar. 0.1 bar means I'm even further away from equilibrium, right? 0.1 bar means the driving force should go up or down for this. It should go up, you know, because I need to form even more product. Whereas if this were, let's say this were 200 bar, this is 200 bars is driving force. So the more product we have, the less the driving force. The less product because we favor a lot of product here. In other words, Le Chatelier's kind of shift. You know, if I start removing product, Le Chatelier's principle says shift it to the right. If I start adding product, Le Chatelier's principle says shift it to the left. That's what we're doing here. And so now the Q's changed here. And so the Q is going to be 0.1 squared divided by 2 squared times 1. Point 1 squared is going to be 0.01. Okay. 0.0025. We plug that in here. That's going to make this more negative and make our delta G more negative. If we add a lot more product here, this will make Q bigger than 1, which makes this more positive, which makes delta G more positive. Well, the same thing here, you know, so I get a delta G that's more negative, means there's a bigger driving force forward. And where's it going to end? It's going to end at when delta G is equal to 0. When is delta G equal to 0? That's when the driving force is going to stop. Well, delta G is going to equal 0 when delta G naught is canceled out by this term, RT ln of, well, if that's 0, this is going to be K. And so when this is going to stop is when Q equals K. When Q equals K, we're going to be at equilibrium. Right now, Q is far from K. And so we can calculate our K. Well, our K is going to be the same thing, 10 to the positive 12. We can see where we're at. And so conceptually, you know, delta G and delta G naught are different things. Sorry, we're out of time here, so we'll stop.